Now that we've seen how adding one of the ions in a barely soluble salt can cause equilibrium to strongly favor precipitation, we can apply this same idea to selectively precipitate one ion out of a mixture of ions while leaving the others in solution. This is called selective precipitation, and it has applications in fields from toxicology to mining. Let's say that I have a solution containing different alkali metals. A 0.037 molar concentration of barium and a 0.0667 molar concentration of calcium, and that I want to separate these two ions completely. Now we do have to qualify that word completely. Even with the arsenic in our last video, the conditions still permitted 2.7 times 10 to the negative 12 grams of arsenic to remain dissolved. It's practically none, but it's not absolutely none. That is too high a standard. But what standard we set really does depend on what our goals are. For this example, let's establish that complete separation actually means that at least 99.9% of one of the ions is precipitated out of the solution. Both calcium and barium form a fluoride salt, but these have different solubility products. Barium fluoride has a KSP of 1.84 times 10 to the negative 7, while calcium fluoride has a KSP of 5.3 times 10 to the negative 9. Since the calcium fluoride has the smaller KSP, that means it's less soluble, and so it will begin to precipitate with a smaller concentration of fluoride than barium fluoride. The higher that we can make the fluoride concentration, the more equilibrium is going to favor formation of calcium fluoride and drive the calcium ions out of the solution. Now at some point, adding even more fluoride will also start to draw barium out of solution, and this is meant to be a selective separation of ions, so we want to pull calcium out while leaving barium in place. To maximize just how much calcium fluoride we can force out of solution, we need to determine how much fluoride we can add until barium fluoride also starts to precipitate. According to the solubility product relationship, the concentration of the barium multiplied by the fluoride squared is 1.84 times 10 to the negative 7. We know the concentration of barium, so we can calculate the concentration of fluorine at saturation, the amount just before barium fluoride will begin to precipitate too. And that maximum concentration of fluoride is 2.22 times 10 to the negative 3 molar. At this concentration of fluorine, barium fluoride is saturated, but the calcium fluoride will be beyond saturated because it had a much lower KSP. The maximum amount of calcium with this much fluoride is 1.08 times 10 to the negative 3 molar. The equation tells us that the rest of the original 0.0667 molar has to precipitate out until reaching this new saturation point. To check if separation is complete, we need to see what percentage of the calcium we extracted from the solution. So the amount remaining, divided by the amount we started with, is 0.016, or 1.6%. That gets most of the calcium, but we're still short of our 99.9% target. Would we have had better luck if it had been barium and magnesium instead of calcium? The magnesium equilibrium formula takes the same shape as barium and calcium, and its KSP is 5.16 times 10 to the negative 11, a much smaller number. There's no change to the amount of fluorine that we can add before barium begins to precipitate, so we just need to calculate the amount of magnesium that can stay in solution with 2.22 times 10 to the negative 3 molar of fluorine. And that concentration is 1.05 times 10 to the negative 5 molar. So 1.05 times 10 to the negative 5 divided by 0.0667 is 1.6 times 10 to the negative 4, or 0.016%, meaning that we can selectively precipitate 99.984% of the magnesium while leaving all the barium in solution. That's within our standard, so we can say that fluoride is able to achieve complete separation of magnesium and barium, or at least complete to within 99.9%.